thunderstorms here producing annuals. Some of the shallow clouds don't precipitate at all. It's kind of chaotic. And every once in a while, sort of like a cancer growing on this state of normalcy, everything gets its act together in a big cluster. And you'll also notice that around the cluster, the air is unusually clear or free of clouds. So we've known about the existence of these clusters. Here's a thunderstorm right here. I don't know if you can see that very well. Here's another one, here's another one, here's another one. These are about 10 kilometers. The whole complex is several hundred kilometers, typically, maybe 1 or 200 kilometers. So we have this clustering. We don't really understand it, but we're beginning to make progress. And we make progress by looking at very, very simple climate states that we can simulate now so well or so finely that we can actually simulate these individual cumulus clouds. So this is a little bit blurry, I apologize, but this is an example of such a computation. You're looking at a snapshot in time of a state called radiative convective equilibrium. It's very easy. You have two processes that you're simulating, radiative transfer and convective transfer. What you do is you start the simulation when typically the troposphere cools radiatively. This is a net divergence of the total radiative flux. And that cooling is compensated statistically by upward convection of heat from the surface. And this happens if you're looking at the vertically integrated water vapor, but you could look at other fields and look at the same as this, more or less. And you just see this sort of random collection of convective cells. If I had a movie of this, which I don't dare do because I'm not proficient with the movie technology, it looked kind of like boiling water, very random. And that's sort of the most primitive climate state. It's horizontally isotropic. In other words, the statistics don't change horizontally. The surface temperature is constant in this line. And you can integrate that forever, and it's in a nice statistical equilibrium state. It has well-defined mean profiles of things like temperature and humidity and so forth. And we've been studying those states for years, but only been able to explicitly simulate them numerically. This simulation is on a lattice, a computational lattice, with horizontal points 1 or 2 kilometers apart, but covering 1,200 kilometers squared. It should be better than that these days.
What are the units?
This is integrated water vapor, so it's probably millimeters of condensed water. Every once in a while, you get a spontaneous phase transition in the state under some conditions, where these are just snapshots separated in time by 2 days. All the convection gets together in a clump. This is a single clump. This is a doubly periodic domain, by the way. So this is really just a single clump. And if the domain is on a rotating planet, that clump is essentially a hurricane. And and if it's not, by the way, if it's not a rotating planet, it still aggregates, but it doesn't aggregate into a vortex. Once it's aggregated, it stays that way. It's a really dramatic change in the physics and the character of the system. One of the things that changes is that the relative humidity, this is simply relative humidity in percent as a function of altitude, it's very humid in an ordinary radiative convective state. After the aggregation into clumps or tropical cyclones, the domain is dramatically drier. It dries things out. And we see evidence of that when we look at observations. This is simply vertical profiles of relative humidity observed in the tropical atmosphere as a function of the different colors here. Is the degree, sort of an empirical index of how aggregated the convection is. The more aggregated it is, the drier the atmosphere. And we know from these numerical simulations, or we think we know, that there are several conditions that are necessary to get this self-aggregation. The background horizontal wind must not be changing a lot with height. We call that image here. You must include the physics of the interaction of radiation and clouds. If you don't have that, you don't get self-aggregation. And water vapor. You have to allow the downdrafts produced by the convection to interact with the surface fluxes. If it's windy, you get locally a higher rate of transfer of heat. just for the same reason you feel colder if you're wet when the wind's blowing, right? More evaporation. And you have to be at sufficiently high surface temperature. If you're at cold temperatures, the self-aggregation doesn't occur. This is just an illustration of that. This is showing the total amount of long wave or infrared radiation going out the top of the model domain as a function of time for a series of integrations that differ only in their surface temperature. So this is low surface temperature, and this is high here. The aggregation occurs in a huge increase in the outgoing long wave radiation, which is a manifestation of that clustering. So at low temperature it doesn't happen, high temperature it does.
Do the simulations correctly get the time scale for some aggregation?
Well, we don't really have a good handle on that empirically. It's not really been studied, but not obviously wrong. I mean, that's all I can say. We haven't really looked at that very carefully. This is all very recent. And if you do the, as I mentioned before, on a rotating planet, you get sort of a tropical cyclone world, okay? You get the whole world is filled with tropical cyclones. And that's nice because it's simple. It turns out there's a remarkably simple scaling that governs this. And that scaling is this, that the spatial frequency of events is the Earth's rotation rate squared, angular rotation rate squared over this potential wind speed squared. That's storms per unit area, if you will. The intensity scales is the potential intensity, as you might guess. And the power dissipation integrated over the main scales as the potential intensity times the square of the rotation rate. So this is a very nice, simple elegant. So we do know what governs the number of tropical cyclones in this extremely idealized world, which is too far from the real world to be able to apply it. But you have to take one step at a time. So we have a little hypothesis going here, which we're testing, which is kind of interesting. And it starts with the observation that at a high temperature, the convection tends to aggregate. And when it aggregates, the humidity drops dramatically in the atmosphere. The main mean. Well, water vapor is the most important greenhouse gas in the atmosphere. So the aggregation reduces that, and that cools the system. But if you cool the system, the convection disaggregates. It's temperature dependent. So it moistens back up, the system warms, and it goes back to aggregation. So all this means that the system wants to be right next to this phase transition between aggregated and non-aggregated convection, which is sort of an example of what we call self-organized criticality in chemical systems. The system wants to be near its critical threshold for self-aggregation. There are predictions that we're in the midst of testing, like the cluster size should solve a power law. That's all sort of ongoing research. If it's true, then this aggregation is kind of a thermostat that works in the tropics to keep the temperature from going up too high. Try to make it too warm. There are a lot of hurricanes, but they dry out the system and thereby cool it back down again. So what we think is the case with tropical cyclones is that we have a kind of a system that looks like this. On this axis is some metric of the number or intensity of hurricanes with some metric of the system temperature. If you're too cold, the only state you're going to see is no storms at all. You have weather noise, you have some PDF of weather noise. And then we think you have at this aggregation threshold a subcritical bifurcation that looks like this. So if you're between A and B in temperature, it's stable unless you push the system. If you, let's say, plant a vortex there, if it's intense enough, it will grow to a fully developed tropical cyclone. So we think you have this. It's well known that tropical cyclones in the real world do not form spontaneously. You have to have an external system to come along to trigger them, literally. That's why we think we live somewhere today in this regime between A and B. All right, very quickly, because I'm running out of time, I want to talk about what we think is going on in the future. And we have an approach that was developed here at MIT to do this that starts from the fact that our global climate models are integrating on computational meshes whose points are typically 100 kilometers apart, state of the art. Well, that's way too big to simulate a hurricane. Now they they do manufacture facsimiles of hurricanes and global models, but they're way too weak and too large to put much weight on. So we have developed a way of deducing, if you will, the hurricane climatology from the coarse numerical output of a global model. And it begins by taking the statistics of the output of this climate model and seeding it with a very large number of sort of proto-vortices, very weak hurricane-like vortices. The second step is to find out where these seeds move. That's easy because to a first approximation, hurricanes move with a large-scale flow in which they're embedded. That large-scale flow is provided by the climate model. Then we run, this is the key step, a very detailed coupled ocean atmosphere hurricane model, which we developed for completely different reasons here at MIT. It's actually been adopted by the National Hurricane Center and other organizations to help predict real hurricane intensity. But we run as a very, very fast model, very high resolution. We run that model over the tracks that are created in the first two steps. And what happens when you do that is about 98% of these seeds are just predicted to die. Very similar to my success rate as an amateur gardener, by the way. I don't know. They just die. And the survivors are sort of considered the hurricane climatology. So it's kind of a natural selection algorithm, if you will, survival of the fittest. And that small fraction is considered climatology. Well, yeah, it works remarkably well. So this is, we can create hundreds of thousands of tropical cyclones easily. This is just 1,000 synthetic tracks created for a simulation of the current climate. And the colors here denote how strong the storms are. Reds are category 5. And it does a reasonably good job. Of course, just looking at a picture like that doesn't tell you that. You have to run statistical tests. This is another shot of Atlantic. This happens to be a subset of hurricanes that will landfall in the U.S. Here is an example of the wind produced by one of these tracks. This is one that affected New York, and this is that the center of the hurricane went up along this black line, and this contours the peak wind experience, peak wind speed experience at every point on the surface. The strongest winds as you expect of a New England hurricane to the right of the track. So all these statistics. It actually also predicts rain. This is storm accumulated rainfall over the whole storm for this particular one event. We have a lot of fun with this. A couple of the surge models. The key thing is it produces the whole intensity spectrum, the whole observed intensity spectrum. So this is just the rate of the number of events in the Atlantic whose lifetime maximum wind speed exceeds the value on this axis. The blue is from observations, the red is from one of the synthetic data sets, and the green are 90% confidence limits. Typically, global models truncate the spectrum somewhere around here. That's where it gets interesting. Almost all the destruction caused by hurricanes is in this tail of the spectrum.
So the blue ones here are real hurricanes.
Yes, that's right. And the red. 211 real hurricanes from 1990 to 2005. And the red is 1,700 and something else. This happens to be just really Atlantic. But we've done these kinds of tests. I could exhaust you with sort of statistical tests that we've been through. I don't have time to do that. However, if you go back to the way we do this, there's something that ties this production of synthetic events to historical storms. We know these historical events to test it.
Well, but you have to have sea surface temperature, though, right?
Well, we have to have a whole climate state that's provided by the global climate model. Sea surface temperature, the winds, the temperature of the atmosphere, humidity, and so forth.
So
That's the drive.
You let the climate model advance.
Yes. Exactly. That's the whole idea. If we seed a particular model in the current climate and then compare its hurricane climatology to the same model run for a future climate or a past climate, like the climate of the Pliocene or something like that. So the idea is you apply this to global climate model simulations. I'm going to show you results that nobody else has seen because we're just in the process of doing this, actually. run for this historical period, 1950 to 2005. Climate models run during that period, and we downscale that climate simulation. And then the same models run forward under a particular emission scenario, in which the radiator force into greenhouse gases increases by about 8.5 watts per meter squared. And so this is the result. We've done this for 5 different climate models, downscale 5 climate models. So this is the annual frequency of events around the world simulated by this technique. And these box diagrams are such that the upper side of the box is the 75th percentile, and the bottom side 25th percentile. It's only from among 5 models. The red is the median, and the whiskers go to the extreme elements of that 5-member set. And so you can see a fairly big increase in activity through the rest of this century, leveling off toward the end of the century. The emissions are assumed themselves to level off then, or slightly before then. This is the sort of spatial distribution of the change in frequency with which tracks go through a 4x4 degree square, lat long square. So most of the increase is in the Pacific, in the Atlantic, and some in the southern Indian Ocean. Where it's white is where fewer than 4 of the 5 models agree on the sign of the change. So it's a weak statistical significance test that fails in these white regions. So significant increases, at least by this metric, in the northern hemisphere and also in parts of the southern Indian Ocean. This is power dissipation showing the same kind of trend, an upward trend through the century, and there's a map of the change in power dissipation over the 21st century, again showing most of the change in the Pacific and the southern Indian Ocean, a little bit of increase in the Atlantic. And you can apply this to other climates. So this compares the current climate to the climate 3 million years ago, during the Pliocene, when the planet was somewhat warmer. And it was before the great ice age cycles began. At least if you believe these simulations, there are a lot more hurricanes during the Pliocene than there are today. Okay, let me summarize. Hurricanes are big Carnot heat engines, remarkably close to an ideal Carnot heat engine. That's kind of fun and interesting. They may be a subclass, what we call aggregated convection, which in other words may have a regulatory effect on the Earth's climate itself, mostly by drying the atmosphere out and getting rid of an important greenhouse gas, water vapor. That's speculation at this point. We have this downscaling technique of embedding very high resolution coupled models inside the output climate models. It seems to work pretty well. The hurricane power has been increasing in the Atlantic, and we project it to keep going up more or less globally as the temperature